All right, class. Well, today we're going to continue our discussion on mass equilibrium, thinking about how molecules distribute themselves now throughout different molecular identities, through different regions of space. And this theory and formalism we're building up is simplified under consideration of dilute solutions. So if we can imagine that the atoms and molecules whose mass transfer we're considering are dilute, like a dilute solution or a gas, then we can work out the partition of function of such a system, and through that partition function get a simple expression for the chemical potential. And we know that if we have a chemical potential, we can predict how mass will distribute itself. So a couple reminders about what we covered last time. So for a dilute solution, the partition function we factorized into two pieces. A piece that had to do with non-translational degrees of freedom. If I have n particles, then n uncorrelated particles will give me n factors of that non-translational partition function. And we isolated all of the translational bit, say by counting spatial degrees of freedom with some resolution delta x. If we had a volume V, then the number of translational states that n particles can explore is V in that resolution, delta x raised to the n, with some factor of n factorial that accounts for permutations. So this was a partition function with a fixed number of particles, volume, and temperature. You might think so the explicit dependence on volume and number of particles is evident just in the equation for the partition function. You might think to yourself, where is the temperature dependence in that expression? You all remember that usually the resolution that we count spatial degrees of freedom is identified with that thermal wavelength, so there's going to be a temperature dependence in that delta x. But likely there's a temperature dependence in those non-translational degrees of freedom too, which would tell me, say, how many vibrational, rotational energy levels I'm populating. From this partition function, we can compute the chemical potential of those solutes as the first derivative of the Helmholtz free energy with respect to the number of particles holding V and T fixed, which is related to the partition function with a factor of kBt, and then the differential of the log of Q with respect to N. And what we get when we take that derivative and we use this trick for taking the derivative of the factorial function and the Stirling's approximation, we get that the chemical potential can be written as a sum of two pieces. This ideal reference state plus kBt log all of the density in some units of a reference density isolated in that second term. So we call this rho naught some standard state density. And this chemical potential then is a standard state chemical potential . This echoes very similarly the structure that we thought through when we talked about things like partial molar volumes, partial molar enthalpies. Those standard state chemical potentials are things that can be measured experimentally and tabulated, which will then provide easy means of computing the chemical potential at a density that you actually care about. So this simple expression, this form for the chemical potential, which isolates the density into that second term, is super convenient. And we started exploring a number of consequences of such a simplistic form. And specifically, we started talking about questions of chemical equilibrium. Imagining that I have some set of reactions that I want to describe their equilibrium constants of. So imagine, say, a gas phase reaction whereby hydrogen gas dissociates into 2 hydrogen atoms. Or maybe how a acid in solution dissociates into a excess proton and its conjugate anion. Or even slightly more abstractly, though similarly importantly, how, say, some protein ligand complex might associate or dissociate. Those are all examples of simple reactions whose equilibrium conditions we can understand by knowing the forms of these ideal or dilute solution chemical potentials. And so let's go back through the simplest example, just this H2 gas dissociated into 2 hydrogen atoms. From the second law, we know if we were to run a reaction forward, say H2 goes to 2 H's, by some amount dN at fixed temperature and pressure, that we can compute the corresponding change in the free energy. If we're working at fixed temperature and pressure, then the free energy we should think about is the Gibbs free energy. The Gibbs free energy is a natural function of temperature, pressure, and the number of particles. What goes with the temperature is minus the entropy. With the pressure, it's plus the volume. And with the number of particles, it's chemical potential. And because I have multiple species, I have a sum over those species. At fixed temperature, the STT term goes away. At fixed pressure, so does the VDP term. So the chemical potential is just a sum of, or the Gibbs free energy is just a sum of chemical potential terms times their changes in numbers of particles. And in the case we're considering here, we have 2 kinds of species. We have hydrogen atoms that are bonded together in the form of H2, or hydrogen atoms which are separated, dissociated from that bond. And the stoichiometry is such that if we were to ask for how many molecules change when I run this reaction forward of H2, well, by construction, I'm losing dn numbers of molecules. And if I lose dn numbers of H2 molecules, then I will gain twice that in terms of the number of hydrogen atoms, because for every H2 molecule that dissociates, I get 2 hydrogen atoms. So the corresponding change in the Gibbs free energy will be the chemical potential for H2 times its change in number of particles, which we just resolved was minus dN, plus the chemical potential for the hydrogen atoms times its corresponding change in number of particles, twice dN. At equilibrium, that sum has to be equal to 0. And so at equilibrium, we find a relationship between the chemical potentials of H2 and the chemical potentials of H atom, namely those have to sum to 0 so that D ends cancel. I'm left with that the chemical potential of H2 has to be equal to twice the chemical potential of H. Again, that 2 reflecting the stoichiometry of this particular reaction. Similarly, we could have worked through this example for the acid dissociation, and had we done that, we would have found that the chemical potentials of the associated acid must be equal to the chemical potential of H plus its anion at equilibrium. Or analogously, the chemical potential of the protein ligand complex would have to be equal to the chemical potential of the protein free in solution plus the chemical potential of the ligand free in solution. And if all of these species are dilute, then for each one of them, we know the forms of their chemical potentials. It's going to be following this dilute solution theory that says that chemical potentials will be a sum of this standard state chemical potential and kBt log the density of each one of those components relative to that standard state. Given these equalities of chemical potentials, we can rearrange that form. So for example, considering our H2 gas dissociation, it would mean the fact that chemical potential of H2 equals twice the chemical potential of H. If we substitute in this dilute solution form for the chemical potentials, we have that the chemical potential of H2 in that standard state plus kBt log the density of H2 must be equal to twice the standard state chemical potential of H plus the term that has to do with its density. If we bring that 2 inside, that squares the density of H. If we group the standard state chemical potentials and define a chemical potential difference in standard state of the reaction as chemical potential in standard state of H2 less twice the standard state chemical potential of H atom, we'll be able to rearrange this and solve for the equilibrium constant of this reaction. Specifically, grouping that standard state piece over on the left, minus that is going to be equal to kBt log rho H over rho naught quantity squared over rho H2 over rho naught. Or finally, exponentiating and taking the kBt over to the other side, we have rho H2 quantity squared is equal to e to the minus beta delta mu of that reaction times a factor of that standard state density. And that is precisely what we mean by the equilibrium constant, which for a gas phase reaction will depend just on the temperature. Right. It's worth thinking through what this standard state reaction chemical potential actually means. Remember, that is the term in the partition function that was inherited from the partition function that came from the non-translational degrees of freedom. If the change in the free energy is equal to mu times dn. If I transfer only one molecule, then the free energy is just then mu times 1, which is mu. If I isolate the part of the chemical potential that doesn't account for translations, that what I'm left with is just the standard state chemical potential. So it has an interpretation as the part of the free energy or the reversible work required to affect this reaction, provided that I keep those molecules from translating. So it's the part of the free energy due to those non-translational degrees of freedom. Sorry about that. All right, so as we were saying, this is the chemical potential, this is the free energy difference for all species at this reference standard state without any of the translational degrees of freedom considered. Okay. Now, note we were able to simplify this expression to end up with this expression at the end, this one here. Importantly, because we were able to isolate all of the density dependence or the concentrations in one part of that chemical potential and all of the non-density dependence over on the other side, this side here. That is made possible only because the species are dilute. You might ask yourself, well, what would change if we did not have dilute solutions? Well, in principle, that would mean that this equilibrium constant would depend itself on concentration. So you couldn't solve uniquely for the concentrations only on one side. Okay, so that's what we had talked about before. You might wonder now, we've spent a lot of time talking about the solutes in these dilute solutions. Can we say anything about what happens to the solvent? Now, it should make some sense that something has to happen to the solvent. If we change, say, the composition by changing the solute, changing the amount of solute present, we're necessarily changing the composition of the solvent as well. So the chemical potentials or the free energies must be functions of both solute and solvent. So let's make some definitions. Let's say that mu sol is the delta G when one solute is added at fixed temperature and pressure. We just noted that the same change in concentration when one solvent would be added or removed. if we wanted to relate the chemical potential of the solute to the chemical potential of the solvent, you all know what equation we should think about. The equation which relates changes in potentials is the Gibbs-Duhem equation. If we remember what that is, the Gibbs-Duhem equation said that S dt minus V dP plus the sum over all the numbers of particles, there are all the species times their changes in chemical potentials. Here we have just solute and solvent. Gibbs-Duhem says that that all sums to 0. At fixed temperature and pressure, those first two terms go away. Rearranging, we find that in solute times d mu solute must be equal to minus in solvent times d mu solvent. So indeed, by changing chemical potentials of the solute, we're necessarily making changes to the chemical potential of the solvent. If I divide through by n, which is the total number of particles, solute plus solvent, I could find a relationship for the change in the solvent chemical potential in terms of mole fractions of the solute to solvent mole fractions, where those have to sum to 1. Now in the dilute solution, the solute mole fraction is very close to 1, so to a good approximation, the change in the chemical potential of the solvent is just minus the mole fraction of the solute times its corresponding change in its chemical potential. Now for a small change in chemical potential, due to small changes in composition, the corresponding change in the solute chemical potential in the dilute solution will be the total differential of the two pieces of that dilute solution form, its standard state plus kBt log the mole fraction. If the only thing that changes is the composition, thus that mole fraction, the change in the chemical potential of the solute is just kBt over the mole fraction of solute times that differential change in the mole fraction. If we were to put this together with this expression for the change in the chemical potential of the solvent, we find that the chemical potential change of the solvent is equal to minus kBt. The mole fractions of the solute cancel, and we're left with just the differential change in the mole fraction of the solute. If we were to integrate this, from the mole fraction of the solute is 0 to some fixed mole fraction, we would find that the chemical potential of the solvent at some fixed mole fraction of solute. Let's remind ourselves that this is also a function of temperature and pressure. Well, that's equal to minus kBt, an integral over the mole fraction of solute from 0 to some fixed value. That will give me some value at 0, which is the chemical potential of the solvent in the absence of any solute. Let's give this a little star. Minus kBt, the mole fraction of solute. So let's write this a little more compactly. The chemical potential of the solvent depends on temperature and pressure and the mole fraction of solute. It's equal to what its value would be in the pure phase less kBt times the mole fraction of solute. So this star value is the chemical potential of pure solvent. What we've just found is that change in the chemical potential of the solvent depends only on kBt times how much solute there is. There's no information about what the solute is over on the right-hand side of the equation, just how much it is. So in a dilute solution, the influence of a solute on the solvent is devoid of any particulars associated with the chemical composition or chemical makeup, molecular identities of those solute molecules, just how many there are. So a natural question is, how does the solute influence the chemical potential of the solvent, given that it depends only on its number? There's nothing over on the right-hand side other than temperature times a number. And the chemical potential is the free energy for moving one particle. A free energy is naturally going to have an energetic and entropic piece. There's nothing to do with the molecule over on the right-hand side, which would arise due to changes in energetics, into, say, potentials with which that solute interacts with that solvent. Rather, there's only a counting term, a term that tells you how many ways have I lost to distribute solvent molecules, given there is some space occupied by the solute. So this influence, this change in the chemical potential of the solvent, is just due to entropy. It's just due to a lower number of microstates that the solute has imposed on the solvent. You call this term an entropy of mixing. In this form, again, the fact that we can work out an expression for the change in the solvent chemical potential in such a simple way allows us to understand implications of how adding some dilute solution, some dilute species to a solution will change the properties, macroscopic properties of the solvent in a way that is impartial to what the identity of the solute is. Those changes, properties of a solution, due only to the number or the concentration of solute in the solution, are known as colligative properties. So these are properties that are independent of solute identity, just a consequence of this entropy of mixing. There's a number of these properties, and let's go through a couple of them. The first is the so-called osmotic pressure. The setup for thinking about osmotic pressure envisions a solution. Let's imagine it's some aqueous solution. We'll identify with this blue color here. So we have a solution of water everywhere in this little box. And let's imagine, all right, try this again. Solution of water in this box. And now let's imagine that in that box, we can put a semi-permeable membrane through which water can flow, but solutes over on one side of that membrane cannot. So this is a rigid semi-permeable membrane allowing solvent to pass, but not solute. Now we can fill that box of solution with a pressure P on one side. And in general, if we were to measure the pressure over on the other side, well, the pressure, if we're not going to have any volume flow of the solvent, has to be equal. But we would notice that there's a pressure on that semi-permeable membrane that is exerted by the solute. The fact that the solute is compressed to one side of this box due to this membrane. It must be the case that at equilibrium, the chemical potential of the solute must be uniform. Because it is able to transverse that semi-permeable membrane. It's able to flow back and forth. We're allowing those states to be accessed in a way that the chemical potential on the right-hand side for the solute need not be the same as that on the left, because we're not allowing it to relax to that side. But for the solvent, the chemical potentials must be equal. So on the left-hand side, we have the chemical potential of the solvent, which is just what it would be in its pure state, just dependent on temperature and pressure. and that's a temperature T that we're fixing, that must equal the pressure, the solvent chemical potential over on the right, which is like it's at a higher pressure and with some solute mole fraction. And we know that if that mole fraction of solute on the right is dilute, that the chemical potential of the solvent will be what it would be in the pure solution, less that kBT times the mole fraction of solute. Now, since the chemical potential in the pure phase at some temperature and elevated pressure is equal to, at first order, the chemical potential in the pure phase at that same temperature and the original pressure, plus pressure times volume per particle. That's just a first order expansion of the Gibbs-Duhem equation, saying that the change in the chemical potential with changing pressure is just the volume per particle, times the increase in pressure, and the increase in pressure here is just this pi. What we have then is this term, pi times V over N, must balance kBT times the mole fraction of solute. At equilibrium, that must be equal to 0. Rearranging, we have pi times V is equal to N mole fraction of solute times kBT, or that pi V is equal to N solute kBT. Pi, again, is the excess pressure exerted from the solute. V is the volume, N is the number of particles and number of solute particles times kBT. What we've just found is that PV is equal to N kBT. Just exactly the form of the ideal gas law, now valid for dilute solutions and the osmotic pressures that they generate. This emerges simply from counting spatial arrangements, just counting up the number of arrangements that solute can occupy. So this osmotic pressure is one implication of this entropy of mixing. Another example is what's known as boiling point elevation. Say at fixed pressure. That is the observation that if I was to take a pure solvent at some temperature and pressure, which was at coexistence, so let's call that temperature T B star for the boiling temperature, star for the pure solution. At that condition of pure solvent, it must be the case that the chemical potential of the vapor at that temperature is equal to the chemical potential of the liquid at that temperature. That would allow me to have coexistence between the liquid and its vapor. If I now then create a solution of the same solvent and now put some non-volatile solute in that solution, such that the solute is only in the liquid phase, what is observed is that the coexistence temperature, the boiling temperature for this transition, will be raised by some amount delta T over what it would be at the pure solution. That's a statement that then the chemical potential of the pure solvent of the vapor at this new boiling temperature is equal to the chemical potential of the solvent at that new boiling temperature and some mole fraction of solute. Now the chemical potential changes with changing temperature, say by some amount delta T. If delta T is small, that change in chemical potential can be expressed as the reference chemical potential at just TB. Let's say this is the side for the solution. So this is equal to what it would have been in the pure solution at TB plus delta T, and the contribution of the solvent chemical potential with non-zero solute. Now changes in chemical potential of either phase with small changes in temperature are given to first order by what they would have been in the absence of any temperature change, minus the magnitude of that temperature change times the change in the entropy of that phase per particle. Again, that follows just from the Gibbs-Duhem equation that says the change in the chemical potential with changing temperature is just the entropy per particle. If I make a small change in the temperature, then the corresponding small change, that change in the chemical potential, is linear in that delta T times the entropy per particle. So if I put this together now, I have the chemical potential in the vapor at the original boiling temperature less delta T, its entropy per particle, at the new boiling temperature of the solution. That then has to equal the chemical potential of the liquid. If I make a change due to change in temperature, it has a delta T entropy per particle for that change. And in addition, there's the contribution from the solute. In the pure phases at TB star, that's where the chemical potential of the vapor was equal to the chemical potential of the liquid. So those two cancel. If I rearrange this, I will have that KB T mole fraction of solute is equal to delta T, the entropy per particle of the vapor, less that the entropy per particle of the liquid, or that the change in temperature due to adding some solute is proportional to the mole fraction of solute, and the constant of proportionality is kBt over this change in chemical potential of entropy when I go from the vapor to the liquid. Well, at coexistence, that change in entropy, if I multiply by T, is just the heat. So that would mean that T times that delta T is equal to some heat. That heat is the enthalpy or the latent heat of boiling. So I get a T times that latent heat. So the increase in the effective boiling temperature at which a solution will boil is higher than its original boiling temperature by an amount that depends proportionally to how much solute I have. Kb, the T's cancel and is inversely proportional to the latent heat of boiling. So the boiling point of a solution is raised by an amount delta T, which depends, again, just on how much solute I have, not the details of what that solute is. So that's another example of a so-called colligative property, a property that doesn't depend on the identity of the solute, just how much it is, a consequence of changing the entropy of the system by adding some other component, which changes the number of spatial arrangements that the first component can adopt. So we'll flesh out these sorts of colligative properties a little bit more in the next lecture, and then move on to more microscopic understanding of solvation and begin a discussion of how one should think about those standard state chemical potentials terms in terms of actual molecular degrees of freedom. Okay, thanks.